Royal Society, OK.
Thank you.
Anything in particular you're doing here tonight, or is it
Well,
just...
I've got to attend some presentation of, you know, the scientist Stephen Hawking?
Oh, yeah, I know you.
Well, I'm doing this program about equations.
Yeah.
And he deals with the enormity of the universe.
Okay.
And his tool for scientific research is the equation, the mathematical equation.
OK.
My name is Matthew Collings. I'm an artist and art critic. That's what I know and understand. But I'm about to enter an alien world. To me, equations have always been incomprehensible hieroglyphs. What do they describe? Are they just a mathematical game? In this film, I'll learn about some of the most important equations in science. They're actually masterpieces that explain the universe we live in.
I would like to thank Dame Stephanie Shirley for commissioning this magnificent portrait. It will be an honour to have my picture join the Royal Society's collection of the greats of British science. I only wish I could remain looking as good as this picture.
With art, I think beauty is very important, and I'm always trying to define it and work out what it is. Now I want to apply that knowledge to mathematics, and maybe understand why scientists talk of beautiful equations.
Hello, Stephen. I'm Matthew Collings. I'm doing this BBC program about equations and beauty.
Hello. That sounds an interesting idea.
Thank you. I look forward to speaking to you.
I'm glad the most respected living scientist thinks I'm onto something. It's a busy night for Stephen, so I've arranged to meet him again in a week's time.
Now, you yourself must work with equations.
I do. I mean, technically I'm an astrophysicist, but
Yes.
I'm really what we call a theorist. What I like to do is noodle around with equations and work things out and make predictions. So equations is what I do every day. I mean, my colleagues who do astronomy like to show pretty pictures and beautiful pictures of the cosmos. I like to show equations, so very much so. Come and visit me in Oxford, and I will tell you all about this. I mean, we can't do this here, but in Oxford we've got blackboards, and I can explain to you the beauty of equations.
Fantastic. Thank you very much, Pedro.
Thank you.
I've come to the University of Oxford to take up Pedro's invitation.
And he's going to tell me about the most famous equation of all, the one that everyone's heard of, E equals mc squared.
This equation conjures up a whole load of thoughts in my mind. But the main ones are that it's got something to do with the atomic bomb, and of course, it's by Einstein. But there's cultural knowledge, and then there's maths. And I don't know anything at all about how E equals mc squared works. When Einstein first published the equation in 1905, it started a scientific revolution.
Hey.
Hello.
Hello, Pedro.
How are you?
Very nice to see you again.
Thanks for coming.
Yeah, well, it's a pleasure. Thank you very much for having me. Now you've got this tall order to explain to me so that I can totally understand it.
Oh, we'll give it a go. We'll give it a go. Let me just clear this up.
Uh-oh. What am I doing? Pedro lives and breathes abstract numbers. I'm an art guy who left school when I was 13.
So what maths do you know?
Well, I must confess I don't know any maths, any geometry or any algebra or anything in that realm of experience. I'm completely ignorant about all that.
Okay.
I know about art, and that's about it.
Okay, that's a good starting point.
Okay.
Let me get a pen.
It seems a very bad starting point for me. But
So you know nothing about what an equation is?
only, I think it's a sort of code or some kind of metaphor for the natural world. It's the natural world reduced to a formula.
That's pretty good. I mean, let's start with a really famous one. Have you ever seen this equation?
Well, I've certainly heard of it. I know it's E equals mc squared.
Very good. E stands for energy. Do you know what energy is? It's a difficult question, so...
You're having energy as you talk to me.
yes.
A certain amount of energy is keeping me alive so I don't die and decay.
Very good, very good.
That's the limit.
No,
That's
no,
what
no.
I think energy is.
No, energy, I mean, energy is it's kind of a funny thing to try and define, but the best way I can think of it is it's the capacity to do things. It's the capacity to lift something up, to heat something up,
Okay.
all right? Then you've got this thing here. Do you know what the M stands for?
I may be wrong. I think it stands for mass.
Exactly, and mass. And mass is basically the amount of stuff in a thing, right? So when you pick up a book, right, it's the amount of stuff that book is made of. And mass is kind of interesting. For example, suppose you've got a nail and you weigh it, all right? And then you leave it out in the air and you weigh it, 3 weeks later, it will have rusted. And so
Its mass has changed.
its mass has
More
changed.
particle things have...
It's gone up, exactly.
yeah.
It's kind of stuff has stuck onto it. There have been chemical reactions. So the mass of, it really does have to do with what it's made of and how it changes. And then we've got this thing over here, the c. Do you know what the c is?
No.
Right. There's no reason for you to know. It's the speed of light. Okay. And c is incredibly important because c is the speed at which light rays propagate through empty space. Okay, so...
I know what squared is. That means a thing multiplied by itself.
Exactly. So this is a kind of fascinating statement. This is saying that suppose you have some mass, right? It's possible to convert that mass into a certain amount of energy, all right? And you need a conversion factor.
I can see that E equals mc squared, like all equations, is about balancing two sides. That's what the equals sign is all about. So this equation allows us to calculate how much energy is contained in any given mass. It's a surprise to me that it applies to everything. Toothpaste, a book, a nail, or uranium for that matter. This equation is universal. And since c squared is such a big number, a tiny lump of matter contains an enormous amount of energy. What this equation doesn't tell you is how to unlock that energy. The most dramatic proof that the equation was true came 40 years after Einstein first worked it out, when the atomic bomb was dropped on Hiroshima. Pedro walked me through the chilling sums.
You have a mass, which is something like half a gram, and I write it as a kilogram.
Yeah.
You need the speed of light, and the speed of light looks like this. It's about 300 million meters per second.
Okay.
Okay, and we can work out how much energy there is. Okay, and all we've got to do is we say that energy is going to be that mass
Yeah.
times the speed of light squared, and what you get is this. Joules. This is the unit of energy. So you get a phenomenal amount of energy. Now, if I told you that this was something like 15 kilotons of TNT, from something the size of a pill,
Yes.
giving enough energy,
Producing an explosion
which is the
of
equivalent
15 kilotons.
tons of TNT, right?
I want to throw you now. I don't know if this is a stupid question and maybe you've got nothing to say about it, but supposing the sign for squared was changed to a 3,
Yes,
would that just be nonsense? Or
it would be
that...
nonsense.
Right.
We'd be nonsense, and the reason it would be nonsense is because we've tested it. We've gone into a lab and we've tested this relationship. We've weighed something, we've done something to it, we've weighed it again, we worked out the amount of energy that came out, and it was on balance. So the left side was balanced with the right side.
I'm impressed that E equals mc squared was created before it was shown to be true. The equation was a prophecy. The 5 symbols explain the link between energy and all matter across the cosmos. This universality is part of its power. Einstein once claimed the only physical theories that we're willing to accept are the beautiful ones. But what do scientists mean by beautiful? They talk about equations being testable, being universal. Is that what they think beauty is?
I'm going to take you to the Rhodes building because Einstein actually came here in, I think, 1933 to give the Herbert Spencer lecture. And it's an interesting lecture because it's a lecture where he basically discusses his philosophy.
Right.
You know, why he does science the way he does and his craft, what he does as a theoretical physicist. And he basically said two things. The first thing he said was that the end game of what he does is experience. It's experiment. It's the natural world.
Right, so it's not theory for theory's sake. It's always relating to the reality.
Exactly. But the bulk of what he says is that what guides him is mathematical beauty or mathematical simplicity. That's what guides his research. And he says it's essential for our point of view that we can arrive at these constructions and the laws relating them one with another by adhering to the principle of searching for the mathematically simplest concepts and their connections. So go for simplicity. Go for the, the simplest relationships which are mathematically true. Right. And that kind of underpins the way that he thought about what he did.
So he was telling people this in a lecture that was really about the philosophy of what he did, what his ultimate aims were, and what the use of what he did was to the world.
Yeah, and it's interesting. It's a kind of practical philosophy. It's what he actually did on an everyday basis. So that's how he worked.
So it gives us an insight, really, into what science at that level is about.
Exactly.
Yeah.
Einstein believed that the laws which govern the universe would have an elegant simplicity, and this would be shared by their equations. I paint abstracts in collaboration with my partner, Emma. It occurs to me that when we intuitively put shapes and colours together in a visual order, we too, like people who come up with equations, try to arrive at a convincing metaphor for nature. For us, art tells you something important about the world. This is a coloured engraving of Isaac Newton by William Blake. It shows Newton studying a tiny corner of the world with a pair of dividers. Blake despised Newton, who he felt reduced the magnificence of existence to cold and mechanistic equations.
So today, I'm coming to a place where I'm actually going to find out a bit more about what Newton actually did.
This is Newton's house, where he developed his ideas on gravity. I'm going back to the 17th century because it's when scientists first used equations to try to explain the natural order.
Hello.
Hello, welcome to Woolsthorpe. I'm Margaret Wynne, the house steward. Pleased to meet you.
Yeah.
Hi, I'm Ruth.
Hello, Ruth.
I'm a Professor of Theoretical Physics from Durham.
Thank you both very much for seeing me.
Yes, it's nice to meet you. And have you been here before?
No, never.
Right.
This is the first time.
Right. Well, this is the house that Newton was born in. Christmas Day, 1642.
Yes. Ruth, the only thing I know about Newton is an image of him observing apples falling off a tree.
Falling from a tree.
And he suddenly works out that that means gravity.
Well, I mean, we call him the father of modern science, and that is not an understatement. We can date our modern way of doing physics or science as trying to write down equations as coming from Newton.
Well, that's very clear, that equations really come from the beginning of equations.
Yes, I think equations as a method, as a means of encapsulating, of modelling, of saying what physics is and what the world around us is.
Why do you think the image of the apples falling is needed in the mythology of Newton?
Well, I think it's the link more than anything else. I mean, if we take an apple and just sort of look at what happens as it sort of goes up and down under gravity, gravity is something that I think we often take for granted. And the apple falling, he realised that the same thing that made that apple fall down to the ground was the same thing that kept the moon going round the Earth, or indeed the Earth.
Realised begs a lot of questions. How does he go from that to realising something about out there?
A lot of hard work.
Is it assuming that perhaps there's some kind of force connected to the moon that's similar to the thing that makes...
That's right, yes. And so as soon as you start thinking about planetary bodies or things moving around other objects, this sort of, I think to people at the time, they would have felt, well, that's a mystery of God. Yes. And we're not supposed to understand that. But by, using this apple as this sort of metaphor for the moon or the sun, Newton managed to sort of say, no, actually man can start plumbing those mysteries.
I'm absorbing everything you've told me, and as I'm starting to freeze a bit,
Shall we go up to
that? But is it, you talked about he didn't want his theories to be thought of as the final word. I suppose it's the nature of theory, it's never the final.
Newton realised that mathematics could provide a precise and universal language to describe things as diverse as the fall of an apple and the orbit of the moon. He put his ideas in a revolutionary book, Principia Mathematica.
I can barely tear my eyes away from this.
That is our very prized possession, a third edition copy of the Principia Mathematica. And if we turn to the relevant page, I'm going to leave you.
Thank you very much. That's wonderful. The first things that we notice here is not a single equation, having talked about Newton as being the father of modern science.
Yes.
The other thing is, of course, it's in Latin, which was the language of the universal language at the time.
Propositio 8, Theorema 8.
Yes, so this is essentially, he is giving us his equation for gravity in words. So he starts off, si globurum duorum in se mutuo gravitantium materia undique in regio univers quae a centris equaliter distant...
Newton's written version eventually formed the basis for the equation for gravity. So I want Ruth to unpick the different elements, a mathematical version of the words.
I notice you have a book there. We could try and translate what he said into one of these beautiful equations.
Absolutely. Find a blank page.
Painting.
Anywhere will do.
Right. So we write both of these objects as M1 and M2. Okay. So these are just the masses.
Yeah.
But then Newton talked about the force between the two spheres, these two bodies, is inversely proportional, which means we divide, to the distance squared.
The two bodies or spheres could be any size, the Earth, the Moon, or even an apple.
And this is G for gravity.
Right.
And it's actually called Newton's constant.
You've written out an equation for me there.
Yes.
And earlier, you threw an apple in the air and it fell to the ground. Can you give me some numbers that will show me what the apple is doing? Yes.
So let's talk about the apple.
Okay. So one of the M's is an apple.
An apple. What does an apple weigh? Half? No, not half. Dear me.
You get a pound of apples, so I guess that's about 4 apples, so it's a quarter of a pound.
We work in kilograms.
200
Yes, let's just say it's 200 grams.
But is the other M the Earth?
I see. You don't
we don't
explaining, do you? You know this already.
I'm guessing. But I don't know how much the Earth weighs, I very rarely buy one.
Well, I can give you a rough idea.
Yeah.
5 times 10 to the 24 kilograms.
Got it.
So
it's 10 to the power of 24.
24, which is a trillion.
Okay, good.
Now, the radius of the Earth is 6,000 kilometres.
Okay.
So
200-gram apple, several trillion kilograms Earth. And radius of Earth, 6,000.
Now, what I'm going to do is cancel all those off to make it easy. Okay. Then what I end up with is a simple 10 on the top times the 0.2 of the apple. So what this tells me is the force the apple feels is its mass times this 10. And this is...
Mass times 10.
10 is... This is the sort of how fast gravity is going to cause the apple to start to fall. So the force on the apple here is simply 2. And that unit is called the Newton.
Ah, N for Newton.
N for Newton.
Fantastic.
The number of newtons measures the force of gravity acting on the apple. It's a complicated equation, but I'm beginning to understand the key parts. The force depends on the mass of the two objects and the distance between them. The bigger the objects, the bigger the force. And the further apart they are, the weaker the force. The two masses, M1 and M2, could be anything. The Earth and the apple, or the Earth and the moon, or the Earth and the sun. Ruth told me Newton's equation allowed us to understand why the moons and planets move around the solar system. His equation seemed to make sense of, well, the universe.
So the equation itself, F is gmm on r squared, that's Newton's equation of gravity. But how we use it, this is a sort of process, you know,
Yes.
of doing science,
Yes.
of calculating things, of making predictions.
You've now shown me how we use that equation.
How we
Yes.
would use it, yes. This is our paint, really, how we paint the world. We paint it in equations. You know? This is, in fact, we use that a lot. We say, I'm painting. You know, we tend to use this word.
Oh,
of
amazing.
painting.
If you can use that metaphor of paint and colours, etc., is there a place also for beauty in this world of calculating things?
I don't expect everyone to find this beautiful, but it certainly is for us and for me.
Great. A few decades after Newton came up with his law, it was used to successfully predict the return of a comet, Halley's Comet. His law of gravity had been confirmed. With his equation, Newton had transformed the way mathematics modelled the world. And his work went unchallenged for over 200 years. Everything changed at the beginning of the 20th century with the arrival of Einstein and his theory of relativity. In that same decade, something else entered, and that was modern art. In the world of art, many believe that Picasso was involved in the same revolution as Einstein.
Weirdly, the one place in which I had heard about relativity before embarking on this programme was art school when I was young. As art students, we all had to absorb the idea that relativity had something to do with cubist paintings. I'm about to look at a cubist painting by Picasso from about 1909, 1910. It's of a woman in an armchair. I think Cubism was really seen as something quite terrifying and shocking when it first came out. It's not like a Renaissance painting where you feel you're looking through a kind of window onto the world. With Cubism, the artist is deliberately confusing you as to where things are and indeed what things are, so that the space in the room seems to be eating into the side of the woman, and the textures of the room seem to be no different from the textures of the woman. So there's all this moving around of objects and space in a way that is deliberately confusing if you were thinking, well, where is the thing that looks like ordinary reality?
I think it's right to say that Cubism was a new kind of beauty that looked a bit like science, but I'm not convinced that Cubism is science. I've arranged to meet historian of science Arthur Miller, who's going to attempt to change my mind.
I've got to tell you, Arthur, that at art school and subsequently, I felt oppressed by the idea that I had to think of a connection between Einstein and relativity and Cubism. Einstein and relativity and Picasso.
But there is one in the sense that, I'll say it, they both worked on the same problem, the nature of space and time.
Okay, the connection is that time and space are important to them both.
That's right.
But where I find the proposal difficult is that just because he's doing something with time and space, that he's therefore something like Einstein, or that Cubism is something like science. I think
Cubism was very much of a scientific research program. As I said, it had an explicit intent to reduce forms to geometry. And Picasso, we know, was influenced.
Why is that scientific and not artistic? I mean, medieval artists reduced forms to geometry, and African artists reduced it to geometry, and archaic art reduced it.
That's because Picasso had in mind scientific texts as a way to do it. For example, we know that he looked at a text written by a mathematician, and the text discussed how you represent in 4 dimensions complex polyhedra. And Picasso took a look at these. Of course, he didn't know what the equations meant, but when the author of the book specialized the equations to 2 dimensions and then could generate illustrations, Picasso was interested in illustrations.
Okay, it's correct to call Picasso a revolutionary artist. It's not hyperbole. But for me, I don't know enough about Einstein to see the way in which Einstein is a revolutionary too, or how Einstein's ideas and Picasso's are the same level of revolution and also going in the same direction.
Well, Einstein was a revolutionary scientist because what he did was to take the next step beyond Newton. Newtonian science is based on our sense perceptions, that all time, your time is the same as my time. What Einstein was able to do was to raise himself to heights of abstraction so he could glimpse a world beyond appearances, the real objective world out there where there is scientific truth.
I still think the connections between Einstein and Picasso are more superficial than substantial, but I am very interested to hear more about Einstein. Arthur will attempt to explain to me one of the key equations of the special theory of relativity. When Einstein came up with this equation, he wasn't even officially a scientist.
The days when he wrote the relativity theory, he worked as a patent clerk in the Swiss Federal Patent Office in Bern. In fact, he worked there from 1902 to 1909. He was also a conscientious daydreamer. And in his dreams and visions, he soared over the landscape of physics and realized what the fundamental problem was, the nature of space and time. And people were beginning to think that maybe there was something wrong with classical intuitive notions of space and time, but they couldn't put their finger on it.
Yeah.
And what they especially wanted to do was to leave alone the notion of time.
Why was time sacrosanct? Because it was obvious what it was, it didn't need any more inquiry, or they were afraid that they couldn't find out anything
It seemed
more?
that your time's the same as my time.
Right.
No matter how fast we're moving with respect to one another.
Yeah, there's no mystery there. We know what time is.
That's right.
They assume.
It's like Superman said, leave time alone.
Right, yeah, don't mess with time.
Don't mess with time, yeah.
Okay, I've got a book, if you've got a pen.
Absolutely. Right. Let me show you one of the spectacular results of relativity theory. And let's do a little thought experiment. Suppose here is mat 1, standing on a train platform.
Okay.
And here is mat 2, just call it Matt, standing on a train. And he's moving along with some velocity.